Today I would like us to discuss stoichiometry of chemical equations, and this is just a study of the ratios that happen between reactants and also products when a chemical reaction is taking place. And to study that, we are going to use acidified potassium permanganate 0.02 m. We will also have oxalic acid 0.05 m. The two substances, they react, and one of the product formed is carbon 4 oxide, but that is not our main business. Our main business is to determine the mole ratio that happens between these two substances. So what we are going to do is we are going to put oxalic acid inside this conical flask, and then we react with acidified potassium permanganate. Then we are going to do the calculations that involves the two substances. Then we find or we determine the mole ratio that happens between these two substances. Now, oxalic acid reacts with acidified potassium permanganate when it is hot. So we are going to measure this one, the 25 centimeters cubed of oxalic acid. Then we are going to heat it, and then we determine the chemical reaction. So let me now have the burner so that I can heat the acidified or rather oxalic acid. This is the burner that we are going to use, and let us suck up 25 centimeters cubed of oxalic acid. So this is the pipette that we are going to use. We put it here, then we heat. We have exactly 25 centimeters cubed of oxalic acid. That is oxalic acid, 25 centimeters cubed. Let us now put acidified potassium permanganate into the burette. Very good. The initial burette reading is exactly 10 centimeters cubed. It is important to record the initial burette reading. So initial burette reading is equal to 10.0 centimeters cubed. Let's now heat our acidified, or rather, let us now heat the oxalic acid. You don't have to heat it to very high temperatures. You need around 70 degrees centigrade. That will be enough. But I don't need to measure the temperature. I can estimate. I don't need to reach the boiling point. That is enough. Let us now start titrating. Our initial burette reading is exactly 10 centimeters cubed, rather 10.0 centimeters cubed. Let us start titrating. Our solution of oxalic acid is colorless, and when the acidified potassium permanganate drops here, it will turn to colorless. But at the end point, this solution will turn from colorless to purple. Let us start titrating. we must titrate until we get a permanent pink color, just a permanent pink color. Let us continue titrating. Let's continue titrating until we get a permanent pink color. We are there. We are there. The solution is slightly pink from colorless. Therefore, we have reached the end point, and our final burette reading is exactly 35.0 centimeters cubed. Therefore, our titer value is 35.0 minus 10.0. We get 25.0 centimeters cubed as our titer value. Thank you for listening to me, and thank you for watching my titration. We have already done titration between oxalic acid and potassium manganate 7, and the results are as you are seeing them. The volume of oxalic acid that we have used is 25 centimeters cubed, and we have titrated and with manganate 7, and the volume of manganate 7 which has reacted is 25.0 centimeters cubed. This we got it from the initial volume we had and the final volume we had. So when we subtract, we get the titer value, which is 25 centimeters cubed. The concentration of the oxalic solution that we used was 0.05 m, while that one of manganate 7 was 0.02 m. Our objective, remember, in this case is to get the mole ratio between these two reacting substances, and this is studied at the stoichiometry of chemical equation. So the equation that we are focusing on in this practical or in this experiment is the reaction between the two substances. And to go through this, we are going to get the number of moles of oxalic acid which have reacted, and later we calculate the number of moles of manganate 7 which have reacted. We get the mole ratio. Then we are going to show that those mole ratios relates the two reacting quantities between the two substances when they are reacting. Let us start by calculating the number of moles of oxalic acid. How do we calculate it? The volume we have titrated is 25. We divide by 1000 to calculate the moles. So we multiply by the molarity. The molarity is 0.05, and the number of moles we get now are 0.006 0.0125 moles. So that is the amount of oxalic acid which have been titrated, and this oxalic acid was in the conical flask, and it was reacted fully with 25 centimeters cubed of manganate 7. Let us calculate the number of moles of manganate 7 which have reacted. So it is 25 over 1000 times the molarity. The molarity is 0.02, and now those are the moles, and the moles of manganate 7 are 0.0005 moles. So we have the 2 moles, or that are the 2 values of in terms of the reacting substances. So now we get the mole ratios. The oxalic acid, that is H2C2O4, the number of moles are 0.00125, while those ones of manganate 7 are 0.0005 moles. To get the mole ratio, we need to divide with the smaller value here. So we have 0.0125. We divide by the smaller value between these two values is 0.005 moles. So we divide by 0.005, and the other side is 0.0005. We divide by 0.0005, and on this side we have 2.5, ratio 2.5, and this side we have a ratio 1. As you know about ratios, here we cannot approximate 2.5 to be 3, or we approximate it to be 2. No, we don't need to do approximation, whereas the kind of ratio we get here is a simple ratio. So we can multiply 2.5 by 10. So on this side we get 25, the other side we get 10. When we multiply this value by 10 and we multiply here by 10, so the ratio between the two substances, or the mole ratio between the two is 25 to 10, which we can reduce further. Here by we cancel by 5 on this side, we get 5. We cancel here by 5, we get 2, and the reacting ratio is 5:2. That is the mole ratio between the two reacting substances is 5:2. Let us now go back to creating the chemical equation, and we have the two substances reacting, that is H2C2O4 in solution form, and we have also manganate 7 in solution form. And remember manganate 7 is acidified. In this case, to know the products, we need to remember that manganate 7 is a strong oxidizing agent, and itself it becomes reduced, and it becomes reduced to manganese 2. Therefore, on the other side, we expect manganese 2. Manganese 2 ions are colorless. That's why the solution of manganate 7, when it was falling on solution of oxalic acid, it was turning colorless, because that's what happens. Manganate 7 is purple. When it meets oxalic acid, it turns to colorless. Then the other product is carbon 4 oxide. So it's another product, and the other product is definitely water. We have water. We have water. And let us now try to create an equation for this reaction that is taking place. We have here the mole ratio. We have found a mole ratio of 5. We have found a mole ratio of 5, so we multiply oxalic acid by 5, and the mole ratio of 2 for the manganate 7. Those two ratios are enough for us to create the chemical equation, because we only now need to balance the atoms. And we start with the hydrogen. Hydrogen on the left is, or rather, not hydrogen, sorry. Let us start with carbon because it's complete on the left hand side. The number of carbon atoms are 10. So we go to the right and we multiply by 10 at the carbon 4 oxide to make number of carbons to be 10. Then we go to manganese. There are 2 manganese on the left, so we multiply by 2 on the right to make manganese to be 2. We want to balance the number of oxygen atoms, and there are 28 oxygen atoms on the left hand side. We want to make 28 oxygens on the right hand side. Already we have 20, because 10 times 2 you get 20. So we multiply water by 8 to make the number of oxygen atoms to be 28. Then we have already balanced hydrogen. Let us now go to oxygen. We have already balanced oxygen. Let us now go to hydrogen. There are 16 hydrogens on the right hand side. We go to the right, we have 10, so remaining 6. So we multiply hydrogen ions by 6, and with that we have created a chemical equation. We have even been able to balance it experimentally by getting the 2 mole ratios, the mole ratio of oxalic acid and of the manganate 7. The 2 are enough to give us the chemical equation, and that's how we can form a chemical equation by performing an experiment, and that is what we are calling stoichiometry of chemical equations. And in most cases those ratios are simple ratios. Like here you can see the ratio between oxalic acid to manganate 7 is 5:2, then is to 6, that is for hydrogen, and so on. And thank you for listening to me. That's the end of that part.